Hello. In this video, we're going to cover section 2.1, which is on visualizing numerical data. Common statistical questions asked about a variable are, what's a typical value? What's common? What's unusual? What's extreme? Examples of variables where we might ask those questions include heights of women, prices of homes, or Boston Marathon times. These are questions about the distribution of the data. The distribution of the data is the way in which the data is organized. The distribution includes the values that were observed in the data and the frequency of those values. Frequency is another word for the count of how many times the value occurred in the data. Distributions enable us to examine the variation or structure in the data. This is helpful for making comparisons between groups, examining data for errors, and even learning about real-world processes. For example, if you had the distribution for the heights of men and women, then you could compare the two groups to see how they differ. If you had the distribution for Boston Marathon running times, and one of the times was 5 minutes, then the distribution would allow you to identify the error, right? You can't run the Boston Marathon in 5 minutes. The first step in examining a distribution is to create a distribution table. The table should contain a column for values and a column for frequencies. Put each of the entries in the value column, then put the number of times that the entry occurred in the frequency column. To help visualize the variation or structure in the distribution, it can also be helpful to put skipped values in the table with a frequency of 0. Okay, so let's try that out. Suppose we had a list of the number of goals scored by NCAA female soccer players in Division III in 2016-17. And this list is just actually part of the number of goals. This isn't all of the female soccer players. It's just a selection. Put the values and frequencies into a table. For any values that are missing or skipped, put those in with a frequency of 0. Okay, so let's go ahead and do that, right? So first thing we look through is we find the lowest value. And if you scan through here, you'll find that 10 is the lowest value. So you want to put 10 first in the value column. And then you check, is there an 11? Yes. 12? Yes. And so on, right? And then even if there isn't something there, you might want to put that in because it will help us visualize kind of in a way the distribution, okay? It'll help us visualize when there is an absence of entries. Okay, and then once you've gone through and you've got the values in there, then we want to put the frequencies next. So we've got 10. We want to count up how many 10s are there. So we've got 1, 2, 3, 4, 5, 6, 7, and I skipped that one, 8. All right, so we've got 8. And then you want to go through, count the 11s, and you should get 7, 12s, and you should get 2, okay, and so on. So that's how you go through and create a distribution table. What can we do with a distribution table? We can try and answer those questions back on the first slide. So let's jump back to those and just take a look at them. All right, so what were those questions? What's a typical value? What's common? Those are kind of the same thing. What's unusual? And then what's extreme? Okay, so if we look at this, we can kind of see what's typical. All right, so based upon the entries, the 10 to 12 maybe, or even 10 to 13, those are kind of the typical values that these soccer players end up, the typical number of goals that we end up seeing from a soccer player is in that range. And then as far as unusual, so unusual is like, occurs less often than common, right? So you see it occasionally, but it's not really rare. And so I would say maybe the next group here would be in the 14 to 16 range. We might consider those to be unusual values. And then the extreme values would be the 19 and 21. So there's a player who scored 19 goals, and there's a player who scored 21 goals. We would consider those to be pretty extreme. Okay, and so that's how we could go through and we can try and answer the questions from that first slide about the distribution of the data by using a distribution table. A visual can make it easier to analyze the distribution of the data. Two useful methods for visualizing distributions are dot plots and histograms. Both use distance to help represent the distribution. Dot plots use dots above a number line to represent the distribution. To construct a dot plot, place stacked dots above a number line where the distance between the dots represent the distance between the values, and the height of the dots represents the frequency. All right, let's take a look at an example of that. All right, so we've got our distribution table, and then we want to translate that into a dot plot. So what we do is we go through and we start off with the lowest value, that's 10, put that in on a number line. And then we want to take the frequency and we want to put that many dots up above the number line. So you've got 8 there. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And then we want to move over a distance and put 11, and then put 7 dots, 12, and then put 2 dots, and so on. Okay, and the distance between the values, right, helps us to visualize the distribution. So we want to make sure that those are spaced appropriately. And then the height helps us visualize the frequency. So from looking at this, we can kind of see what's typical or what's common. This is the typical or common range where you see a lot of dots stacked above the number line. And then unusual would be where that kind of starts to taper off. And then extreme would be the guys that are off all by themselves. Histograms use bars above a number line to represent the distribution. The bars group observations into intervals called bins. The bins divide the number line into equal width segments. The height of the bars represents the number of observations that fall within each bin. So to construct a histogram, we want to first divide up the number line into equal width segments. These are going to be our bins. Next, count how many observations are in a bin and make the bar above that bin have that height. If an observation falls on the boundary between the bins, then you just want to follow a consistent rule for which bin to use, the bin on the left of the boundary or the bin on the right. Okay, so let's say we were going to go through and construct a histogram. Here's our data. The first thing that we do, we start off, we go on the number line here, and we want to break up the number line into equal width segments. Okay, so a default way to do this, a good guess might be to go through and say, how about bin widths of length 2, right? So we go through and we have 10, 12, 14, 16, 18, 20, and 22. So that's the first thing you do. If you're going to go through and construct this, is you break up the number line into these bin widths. Okay, and then once you've done that, what we do is we go through and we figure out how many observations are in a bin. Okay, so since we're starting with 10 here, obviously the bin to the right of 10 is where we're going to put those observations. So we've got 8 and then 7. So that gives us 15 observations that fall within that bin. And so we want to create a bar that has height 15. So that's what you can see that has been done here. And then 12's on the boundary, but just like when we did 10, we put it into the bin to the right of 10. So 12, we want to put it into the bin to the right of that. And so we've got 12 and 13. Those are going to go into that bin from 12 to 14. Okay, but not 14. So 14 is going to go to the right again. So you want to follow a consistent pattern there. So we take 12 and 13. That gives us 9. So we want to draw a bar that has height 9. Okay, and then from 14 to 16, that's going to include observations at 14, again, to the right, and then 15, but not 16. 16 would go into the next bin. So we've got 4 and 2, that gives us 6. So we want to draw a bar that has height 6, and so on. That's how you go through and construct a histogram. All right, so the bin width, let's think about this for a second. So determining the width of the bins is more art than science. If the width is too low, then the histogram resembles the dot plot, okay, with very spiky bars. That's actually not the desired outcome. We have the dot plot for that, okay? If the bins are too wide, then the distribution of the data is not really visible. We can't really infer anything from the example that's there, where you have bins of width 6. Okay, so what you want to do is you want to try and find something between the two. And it's not always going to be perfect, and not every single person is going to agree. There's some art there. So you could go back to the previous examples. You know, was 2 the right width to go through and interpret the results? Or maybe 3 would have been a better choice. You know, figuring that out is, again, it's part of the art. Rather than have the height of the bars represent the number of observations in a histogram, it is also possible to have the height of the bars represent the relative frequency. Relative frequency is a fancy way of saying the proportion of the total observations. In the relative frequency histogram on the next slide, the first bar contains 40% of the total observations. To construct or translate a histogram to a relative frequency histogram, you want to divide the number of observations in each bar by the total number of observations. All right, then the heights of the bars should be the same in the two graphs. So here you can see we've got on the left, we've got a regular histogram. On the right, we've got a relative frequency histogram. Notice they have the exact same shape. Okay, the only thing that changes between the two is that instead of having the number of observations in each bar, instead we have the percentage or the proportion of the total observations that's in that bar. Okay, so in this case, if you go through and you take 15 observations, and then you go through and you divide by how many observations there are, you're going to get 0.4. So that's the percent, 40% or 0.4 proportion of the total observations is in the first bar. The second bar has, looks like about 25% or 0.25 proportion, and so on. Okay, so that's a relative frequency histogram. Let's look at an example from the homework. All right, so here we have a dot plot that shows the cholesterol levels of 108 adults from 2010. We're told a cholesterol level above 240 milligrams per something, I don't know what that stands for, is considered unhealthy. How many people in this group have unhealthy cholesterol levels? So we're asked to go through and find that. And then once we're done with that, what percentage of the people in the sample have unhealthy cholesterol levels? And then how does this compare with an estimate from 2010 that 18% of people have unhealthy levels? So how would we go through and figure out, using the dot plot, how many people have unhealthy cholesterol levels? Well, we're told that anyone above 240 is unhealthy. So we can go through and we can look on the dot plot. We can find where 240 is. So here we've got, there's 200, there's 225, there's 250. So 250 would be the first group that would be above the 240 level. So what you want to do is you want to count up how many dots are at 250, 275, 300, and so on. Count up how many dots are there, and those are going to be the individuals that are in our dot plot that represent unhealthy cholesterol levels. And then once you have that number, we want to go through and then divide that by the total number of dots. So we hopefully you don't have to count those up. In this case, we're given that there are 108. Okay, so you want to take that number that you got from this question, divide by 108, and that'll give us the percent of the individuals in the study who were unhealthy. And then we can go through and compare that percentage to 18%. All right, so on the next page, we go ahead and do that. So to find, we want to count up the number of dots above 240. I've done that for you. That's 27. And then to turn that into a percentage, we want to take that and divide it by the total number of dots, which are 108. We get 25%. And then we can go through and interpret the results and say 25% is larger than the estimate from 2010, which, you know, the way that you could use that in the real world is that it puts the estimate into doubt. It makes you question the estimate. Now, just because you've taken one study of 108 individuals, that doesn't nullify the estimate, but it would maybe suggest that we should do more research to check, is 18% really the level of individuals who have unhealthy cholesterol levels, or is it closer to 25%? Only with more data collection could you figure that out. Okay, that's the video. Thank you for watching, and I'll see you next time.